Happy New Year, everyone. Welcome back. We're going to take a few steps backwards today and deal with more rigorous type stuff in our course. Over the past couple of lectures, we've been dealing with interactions in quantum fields, and we've been finding it harder and harder to rigorously justify the calculations we've been making. Nonetheless, we've come to a kind of close in the topics. We managed to discuss the scalar field and argue pretty compellingly that the Klein-Gordon field gives a unitary representation of the Poincare group. Then we acknowledged that the scalar field isn't really a good model for nature, and we introduced interactions, and then we approximated various quantities via perturbation theory for these interactions. And then we introduced the formalism of Feynman diagrams to deal with this ensuing chaos of terms when you do the Taylor expansion for the propagator. Well, we're going to stop our discussion of interacting quantum fields and go back to free fields for the next couple of lectures. And we're going to do so in order to talk about a kind of particle that hasn't come up yet in this course, namely a fermion. So we could talk about scalar fermions, but we're not going to. That's something that will come up in the next course under the topic of ghosts. Instead, in this course, we're going to talk about actual fermions that we see in experiments, namely electrons and positrons. So we know that they carry a spin, intrinsic spin, and we need to build remember our objective in this course is to build relativistic quantum theories and we've been so far focused on scalar particles. We've built relativistic quantum theories of scalar particles. Well, today our objective is to build a relativistic quantum theory of fermions. And to do that, we're going to need to go right back to the representation theory of the Lorentz group and try and find representations which have an intrinsic spin. So up to now, our scalar particles have carried no intrinsic spin. So if you recall, we have this Lie algebra for the Lorentz group. And the strategy to build relativistic quantum theories. The first thing is to build relativistic classical field theories. Which involves finding representations of this Lorentz group. Then we guess a quantum theory called the quantization. basically by putting hats on all of the operators, or all of the functions that we write down. And then we check that we get a nice projective unitary representation of the Lorentz group. That's a strategy that we have for building, at the moment, relativistic quantum theories. There's other strategies you could adopt. You could start by assuming you have one of these and somehow work backwards. It's a viable strategy. You could simply not bother with the classical thing and just guess wildly until you get successful. Or you could work with these things here and not really care if you're getting a unitary representation of the Lorentz group. As long as things are matching experiments, you could be happy. There's various strategies to build relativistic quantum theories, but this is the one we're going to adopt in this course. And I freely admit that this is not really the nicest logical progression to start with something classical and then guess, but it's certainly one of the more productive ways to approach the problem. And so now we're going to spend today, I think, most of today just doing this. We're going to be building a relativistic classical field theory for a fermion type field. And that field will be called the Dirac field. But to do that, we need a classical field, right? So we need some kind of Lagrangian. We're going to want to write down a Lagrangian density for a field that's appropriate for fermionic quantization. And since we know that fermions carry an intrinsic spin, like electrons, positrons, muons, then we're going to look for a Lagrange density for a field which has some intrinsic angular momentum. So that forces us to look for representations of the Lorentz group that have a higher spin. And that's where we're going to start with these relations here. Because we know that if we can get a representation for the Lie algebra, then we can exponentiate that representation to get a representation for the Lie group. So I'll write that down. So given a set of objects J mu nu obeying these relations up there, these objects will be matrices. We can get a representation of the Lorentz group by exponentiating these matrices. They'll be 4 by 4 matrices in our case. And then we're going to look for Lagrange densities invariant under these transformations. That's the general strategy. Okay, super. But that forces this question on us: how do we build these things? How do we find matrices J mu nu which do the right thing, which obey this Lie algebra here? And I'm going to show you at this stage, I'm going to show you a trick. I don't consider it obvious what we're about to do. By no means obvious. You can check everything all right. It's very easy to check. But how you would come up with this in the first place would require you to think like Dirac. But once you've got it, then it works out very nicely indeed. Okay, here's how it works. Suppose we have a set of 4 n by n matrices gamma superscript mu. And it's not just any set of 4 n by n matrices. They have to satisfy a certain anti-commutation relations algebra, namely this one here. I've been using Ada in this course, haven't I, so far, for the metric. I realize I come back in 2017 and the metric changes its name. Yeah, Ada is what I've been using. Right? I think that's been consistent with what I've done so far as eta. Okay, if you see me writing G superscript mu nu, please say something, just so we can keep the notation as consistent as possible throughout this course. All right. Suppose we could find a set of 4 such mythical beasts that obeyed this anti-commutations relations algebra. Then it turns out using these guys we can build a non-trivial representation of this Lie algebra here for the Lorentz group. And it's a slightly tedious calculation, but it's, and I guess I'll leave some of it as a exercise. So it's an exercise to show that these objects here obey this Lie algebra. And I've done it here in my lecture notes, and it's surprisingly tedious. I'm looking over half of a page of calculations here. I mean, it's not that, there's no complicated step anywhere along the way, but it is sort of tedious. I will leave that to you to do, but I guess I'll start with a hint. Will I? No, it's just by direct substitution and using this anti-commutator property over and over and over again. It's mostly tedious. So, show these 16 objects obey star. Well, what can we say about these 16 objects? Well, there aren't 16, right? What happens when mu equals mu? What do we get? Commutate, yep, 0, that's what we get. So there's certainly no S mu mu. And in fact, what happens if mu is less than nu, then that's just the same as minus S of nu mu. So in fact, this is kind of nice. I mean, you can already see that this is about right in terms of the number of degrees of freedom. There are precisely 3 times 2 times 1 of these objects. So there's 6, right? And that's exactly the number we need for the Lorentz group. So all you have to do is convince yourselves that this works. Now, for the Lorentz group, for 3 plus 1 dimensional spacetime, I mean, there's a Lorentz group for 1 dimensional, for 2 dimensional, for n dimensional spacetime. These gamma matrices have to be bigger than a certain size. Like this doesn't work for 1 by 1 matrices, right? You can already see that. So there's no way to find a set of 4 1 by 1 matrices which obey this algebra. Pretty tricky. Because, well, okay, trivially, yes, they're all 0. And what about 2 by 2? You might wonder, maybe it's possible to find a 2 by 2 matrix gamma mu that obeys, and then when you build these things, it obeys this Lie algebra here. Well, you probably quickly convince yourself that's not possible because there's at most 4 linearly independent 2 by 2 matrices, and we need like 6 operators to come out. So 2 is not going to work. 3 is a maybe, but you can check that that doesn't work either. And in fact, 4, n is 4, is the minimum you need these matrices to be 4 by 4 before we get a non-trivial solution to star. And the representation we're going to use, I'm just going to tell you what it is. Actually, it's kind of nice to work out how to build these things in general. I guess I'm not going to resist the temptation to tell you how to build gamma matrices, but I'm going to show you this answer first. So our representation, there's 4 of them. We have one called gamma naught, and gamma naught is a 4 by 4 matrix with an identity here, 0, 0, 0, 0, 0, 0, 0, 0, 0. That's gamma naught. That was easy. Then we come to gamma 3 more, and these further 3 gamma matrices here are given in terms of the Pauli sigma matrices, which I'll write out in 1 second. Okay, so these are, let's say, 1, and I believe there's a factor of a half. So I didn't write out the representation of the Pauli sigma matrices we're using, so I'm going to put a circle around here, and if we find a mistake, I may have to correct that constant of proportionality there. So according to this recipe here, we're going to be able to build some nice 4x4 matrices which obey star, these relations here. That's our objective. And let's start writing them out then. So it's naught j. What are these according to this trick? Well, they're I over 4, times by the commutator of sigma 1, gamma naught, and sigma j, gamma j. Blah. And that gives us the following representation. That's 3 of the Lorentz group generators, the algebra generators. They're the ones that generate boosts. And we need 3 more, right, to generate rotations. And then we're done. So let's get to that in the next step. Let's write out the other ones, the rotation generators. Interesting. So this is what we get for the rotation generators. Substitute this formula for the gamma matrices in there and compute a commutator, and we end up with this expression here. And that, of course, comes from the fact that the Pauli matrices obey these commutation relations here. And now we'll find out if I made a factor of 2 mistake. So let's do x, y. Okay, I don't believe I made a factor of 2 mistake. I think that's correct. 2 times this, of course. Although this factor of 2 here makes me wonder. Okay. Well, let's work this out then and see if there is indeed a factor of 2 problem. So let's do the example of S12, which corresponds to this calculation here in a minute. Okay. Okay, so there's definitely a factor of 2 missing in the definition I've been using for the Pauli sigma matrices, which is annoying. So let's correct this. That is 1. And then that becomes a 2 here. And then in this calculation here, where we encounter the commutator of sigma 2 and sigma 1, we pick up an extra factor of 2, and that's the one that we're missing. And all is good. So it checks out with what I've written before. Yep.
In the general definition of our SJK up there, in the matrix, isn't there a minus missing?
in the general definition of the SJK up there, is there a minus missing? I will just check that. I think you're right. I think there is a minus missing. Thank you. There's definitely a minus missing there. Yeah, but otherwise I think this is now correct. So I think we've got the correct normalization now. We'll stick to this for the rest of this course, I hope. This is the one I would usually use without the factor of a half. It's in this representation that the Pauli sigma matrices are Hermitian and unitary. Which is kind of useful for building all kinds of things. So I'll say a couple of words about how you might build matrices that satisfy these anti-commutation relations. Just a couple. And to do this, we use a trick called the Jordan-Wigner transformation. So it's sort of sufficiently nice trick that I think it's worth telling you about it. So we'll call this star star. So this is a very useful thing that I'm going to tell you about. That will come in handy in all kinds of places in physics where you have to deal with fermions. So the problem with fermions is that they obey anti-commutation relations, and these, you can smell the fermions here. There's an anti-commutation relations algebra. And then if you have things that anti-commute with each other and you want to put them on your computer, and your computer only understands linear algebra of matrices, how do you represent these things on a computer? So we'll start with this. So I know that there's a minus sign in here in the metric, but we're going to start by trying to solve these equations here. So suppose you want to find some represent operators obeying this relation here. And A is, I don't know, A can be whatever. A can go from 1 to all the way up to n. So there's this really fantastic trick to represent operators that obey this algebra on your computer in terms of normal matrices. And it's called this Jordan-Wigner transformation. And it relies on these three guys here, these Pauli sigma operators. So you set mu1 equals these have to be, yeah, that's annoying, yeah. So, okay, well, we'll do it like this. There has to be a dagger, otherwise it won't work. But then I'll argue how to get that from knowing this. So you set mu1 equals to Pauli sigma plus. So I haven't written that down yet, but I'm going to tell you what it is. It's this matrix here. It's a 2 by 2 matrix. And then you set mu2 to be Pauli sigma z tensor Pauli sigma plus. So these have to operate on the same space, so actually I'll write it like this. Okay. So you can check that sigma plus anti-commutes with sigma z. So this operator mu1 anti-commutes with mu2 dagger, no problems. And you can check that the commutation relations between mu1 and mu1 dagger are not quite these. Well, we'll fix that up. Oh, no, it's exactly correct, yeah. So mu1 okay. And there's nothing stopping you from exploiting this trick to build even more such operators. So if you tensor on another I here, then we can find a mu3 which obeys all these relations here as follows. So you take sigma z, you tensor it with sigma z, and then you tensor it with sigma plus. And then you can check that this guy anti-commutes with this guy. It anti-commutes with this one. This one anti-commutes with its adjoint to give the identity, as does this one, as does this one. And in fact, this trick works forever. And that's how you can find a bunch of operators which obey the fermionic canonical anti-commutation relations, but they're matrices that you can input into a computer. So it's a representation of those relations. And the trick to represent these is hardly any different. So I'm going to show you a relatively inefficient way to represent these gamma matrices, but you can break them down into representations, the representation we've been working with here. So the trick is to find operators that anti-commute with each other. That's really the difficult bit, and the Jordan-Wigner transformation is the thing that does that. Once you've found a bunch of operators that anti-commute with each other, then everything else becomes making sure you get i's in the right place. I believe that's the metric we're using in this course. Is that correct? Does anyone remember? Yeah, someone does. Good, thanks. So we could take some inspiration now from what we've written, see where we get. Okay. Sigma x. Now we want to find an operator which anti-commutes with sigma x. And we know one, that's sigma z. Sigma z always anti-commutes with sigma x. That's the nice thing about the Pauli operators. They anti-commute with each other. That's a property that I'll actually write down. I guess I didn't say it completely out loud. Yeah. Should write it down now. These Pauli operators have this very nice property that they anti-commute with each other, except when j equals k. And actually, once you see that, it's kind of clear what to do, right? You need to find a fourth one that anti-commutes with all these three here. And so this is what we're going to take as our fourth gamma matrix. We need something that always anti-commutes with that. Sigma z is a good candidate, and yet obeys this algebra, so sigma j like this. So we see that gamma naught anti-commutes with gamma j for all j, because x anti-commutes with sigma z. Gamma naught squared is going to be twice times the number, the identity, which it is in this representation here. But these gamma j squareds, they've got to be minus times the identity. So we have to put in an imaginary number like this. And then I think we recover the representation that we've been using so far, which I erased, huh? Yeah. We don't, because I used the y. Sorry about that. It's the y. Now, if you have these relations just in 4 dimensions, that's how you can do it. But if you have it for larger dimensions, this trick generalizes. You can use this observation here about these strings of sigma z's to build, or what sigma y's, we could have put here equally sigma y's, to build representations of these so-called Dirac matrices in any dimension that you like. Good.
Do we have to change now the gamma 0?
The question is, do we have to change the gamma 0? No, because we only need that gamma 0 anti-commutes with gamma j, and because of this line here, x anti-commutes with y. So you can put here y, z, or any linear sort of rotation thereof in the yz plane, and that will work. I work with z over here. That was a bit unlucky. I should have put y's here. It would, the same thing works if I put y's here.
But x, y, and z are the same like 1, 2, 3, right?
X, y, and z are the same like 1, 2, 3. Well, yes. Yeah. X is 1, y is 2, z is 3, yeah. Yeah, gosh, sorry about that. Now I see, yeah. Yeah, you have to get used to this, I'm afraid. So I'll write that here. Sigma 1 is sigma x. Yeah. This is quantum information notation. This is high energy notation here. So that's why I'm slipping between the notations without noticing it. Right, so the Pauli operators are kind of like the atoms of these fermionic type anti-commutation relations. And there's a reason for that. They also give a representation of the quaternions. But I think that's, well, I'll just say that. And just leave it at that. That's a sufficiently mysterious statement that I don't think it's very helpful, but I'll leave it there anyway. Maybe one day you'll appreciate it. Well, I can give you a little bit of background while I raise the board. Quaternions give a very efficient and compact way to do rotations in 3 dimensions. So if you do any form of computer graphics and you need to do 3D projections and manipulate 3D representations, and you need to do rotations of 3D objects, then using quaternions is really the most efficient way to do that. And so this connection with rotation, the rotation group lies at the heart of this mysterious statement there. All right, let's give these things a name. I've said it before, but we should say it anyway. If you have a bunch of things obeying star star, they're called Dirac matrices or Dirac operators. I prefer Dirac matrices because we're going to have Dirac operators in a different context. And a 4-component object transforming according to the representation of the Lorentz group given by S is called a Dirac spinor. So I write that now. Such things exist, right? Because we found 4x4 matrices which represent the Lorentz-Lie algebra. We can exponentiate them. And we get 4x4 matrices. Therefore, there are things that transform according to these 4x4 matrices, and we call such things spinors. Not spinors, they are called spinors. That's where speaking German helps. You wouldn't say Spinor, you would say Spino. So it's a false friend in some sense to think that you should change the pronunciation to Spinor when you say it in English. I freely admit that the first time I saw this word, I hadn't heard anyone say it out loud, and I thought it was Spinor. So. But no, it is not. There we go. Now we're going to immediately jump to fields, to classical fields of spinors. We start off with this transformation law here, and now we're going to build a field corresponding to these objects. What is a spinor field? It's a map from space-time to the four-component objects here. And here's where it gets really annoying, right? An element of this thing here called a vector space would be ordinarily called a vector, right? Because if a vector is an element of a vector space. But in high-energy physics and in relativistic physics, we call something a vector if it transforms in a certain way under the Lorentz group. So this is collision of terminology at this point here. So spinors are vectors in the sense of belonging to a vector space, but they are not vectors in the sense of transforming as vectors under the Lorentz group. Yep, question?
I have to admit, I don't really understand what do you mean by saying C transforms according to the transformation. What does that tell me about C?
So the question is, what does it mean C transforms according to this transformation here? Well, it means that we define psi in another basis, in another reference frame, which is related to the original reference frame by these boost and rotation parameters here, according to this law. This is actually a definition. If I have a psi in one reference frame, and then there's another reference frame related to the original by a boost or a rotation or whatever, then the way that C is defined to look in this other reference frame is as the original one multiplied by this matrix here. So this is actually a definition. So I think that there's a lot that sort of is potentially misleading about the words transforming according to, which you'll hear people say a lot. Transforming according to really means that I hereby define that in different reference frames, this object looks like this. And I'm going to use this terminology throughout the course, so you have to get used to it. As I'm about to now. So spin of field is defined to look in different reference frames according to this formula here. Now we'll have to talk about this formula a bit to justify some notation. Because we've got two different 4x4 matrices associated with the Lorentz group appearing in this definition. This is the usual representation of the Lorentz group here, these J mu nus, the one we've been using with the zeros and the ones and the minus ones that I introduced way back in lectures 4, 5, and 6, I think. So this is your standard representation for a Lorentz transformation right here. And this is our other representation for the same Lorentz transformation. So the subscript half here is meant to tell you this is another representation for exactly the same Lorentz transformation as lambda. That's why these omega, these boost parameters and so on, are the same between these two. So that Lorentz transformation represented by this in the usual way, when it acts on a spinor field, acts like this. So remember, this 4x4 matrix here is different from that 4x4 matrix there. They're both 4x4 matrices, they both obey the same algebra, but their entries are different. So that's how we're going to define a spinor field, to be an object that in different reference frames looks like that. We're going to use the Einstein summation notation. For these repeated indices. Now, every representation of the Lorentz group is a remarkable thing and can be used to build field equations. We want to build Lorentz invariant field equations. That's our ultimate aim, because once we've done that, then we can write down a Lagrange density. We can then quantize the system by putting hats on it and hoping that everything works out. If we cross our fingers and say la 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 loud enough, it might work. And the way to build these invariant equations like this is to exploit the remarkable properties of representations of the Lorentz group. So your first guess might be just the Klein-Gordon equation. That's actually invariant, right? Okay, there's a little calculation to do here. In a different reference frame, it's still obeyed. That's a little exercise. It's not a very hard one, right? Because you just have to prove to yourself that these lambda half rules don't interfere with these four equations here. And they don't, it's all linear, so it's fine. But there's a far more remarkable equation you can write down, and it took really the genius of Dirac to spot this one. And to write down this second equation, this second invariant equation, we're going to need an auxiliary computation that we have to do right now. So we have these gamma matrices, these 4x4 matrices here, and the computation we need to carry out in order to convince ourselves that the equation we're going to write down is correct is this commutation here. And it turns out, and that's a lovely exercise for you, that this is given by the following formula. I'm not very efficient at these kind of calculations. It took me 9-10 lines to do it. But there are plenty of tricks you could use to make it quicker and more elegant. So when you see this, well, you should really begin to start to get a feeling for how this calculation is going to work. I don't know. We'll see. What this equation is meant to make you think of is the transformation of vectors under Lorentz transformations. I admit it's slightly obfuscated. So let's write out the exact same to first order. Take this identity here, and we're going to use it to deduce that this is true to first order in the smallness of omega. So if you exponentiate this, which means do it over and over again with smaller and smaller omegas, then you'll see that that's equivalent to this equation. And this is the equation that should produce vibrations. No, I got the minus one here. So this tells us that the collection of 4 gamma matrices, if you look at the index as like a vector index, then under Lorentz transformations, this collection of 4 gamma matrices transforms exactly like a 4 vector under Lorentz transformations. These matrices do. And it's that observation which should just directly lead us to an invariant equation. Because once you've got a vector, if you can contract it against another vector, you get an invariant object. And it just so happens that the differential operator d mu transforms just about the right way. Oh, I haven't erased that. So if we contract d mu against gamma mu, we're going to have written down a differential operator that is invariant under Lorentz transformations. So before that, I just going to set the notation here. Yeah. And this leads us to an invariant equation of first order, not second order. Remember, Klein-Gordon equation is second order. For this Dirac-Spinner field. We're going to, in 10 minutes, yes, we're going to show that this equation is invariant. But before I do that, I just want to tell you what it is as a thing. This is an operator in the sense that it's a 4x4 matrix of partial derivatives in each row and column. We'll write out a couple of entries of this 4x4 matrix. If you expand it out, that's what the Dirac equation looks like. And now we have to got to be careful with the indices here. And we can take a look at what the actual entries of this 4x4 matrix of partial derivatives looks like. So let's just focus on this one here. Remember gamma naught looks like this. So that implies that I gamma naught delta naught looks like this. And so on for the other terms of the Dirac equation. So it's just some gigantic 4x4 matrix of partial derivatives with i's and minus signs littered about. And now we're going to prove that it's actually invariant. I mean, it's basically invariant, obviously, by the fact that it's a scalar under Lorentz transformations. This transforms as a vector, so does that. We're done, right? But it's worth doing it explicitly just to see how these calculations go. So under Lorentz transformations, we know that a Dirac spinor field goes like this. And we know that d mu transforms like this according to the inverse. Because it's got a downstairs index. And we're going to substitute those two transformation laws into the Dirac equation, and, well, we'll see that everything's okay. So let's look at the left-hand side now. I gamma mu d mu minus m psi. That gets transformed according to these laws here to something different. Just substituting in the transformation laws we've already written down. Let's insert the identity. Doing nothing is always a legal operation, unless you want to get paid. All right, this is fantastic, right? Because now I've got a lambda a half to the minus 1 times by gamma mu times by lambda to a half. Because this linear operator here just commutes with numbers, I can move that past it. And then over here, this m, that's just m times the identity. I've got lambda half times by lambda half to the minus 1, which gives me lambda half. And now we can use the fact that this thing transforms as a vector under this adjoint representation. But look at this object here, lambda to the minus 1 d mu differentiated with respect to lambda to the minus 1 x. Feels like a delta function. That's exactly what it is. And we see that in our new reference frame, this equation is satisfied. And hence the Dirac equation is invariant under Lorentz transformations. Got a couple more minutes. I'll show you now that the Dirac equation contains the Klein-Gordon equation. So it's strictly stronger. So suppose we have a solution to the Dirac equation. Well, we're free to multiply our solution by whatever operator we like. So it's certainly a true statement that if the Dirac equation, psi is a solution to the Dirac equation, that's 0. So applying whatever we like to 0 will always give us 0. So there we go. We apply that strange looking operator there, which is almost the Dirac equation, to something that's already 0. And the whole trick here is to multiply out this bracket and then use the rules for the gamma matrices. And we learn that fact when you multiply out both sides of that equation. But we know what the anti-commutator between gamma mu and u is. By definition, it's 2 times eta mu nu, which raises that index and then gives us the Klein-Gordon equation. So the Dirac equation is a stronger condition on the components of psi than the Klein-Gordon equation is. The Dirac equation is first order in time, which is very interesting, first order in all the components, in fact, whereas the Klein-Gordon equation here is second order. I guess I'll put a box squared to make it really clear that it's second order. And that shows itself in the solutions to the Dirac equation as well. You get different quality of solutions. Now, it's tempting to think that the Dirac equation is some kind of relativistic single particle equation, but there's really problematic operational difficulties if you go down that route. And so there's no point, in my opinion, in teaching you about the Dirac equation as a single particle equation and then turning it into a field theory if we're just going to turn it into a field theory in the end anyway. So that's why I've been insisting throughout in calling this a field equation and psi as a field, not as a wave function. So you shouldn't think of psi as a wave function for a particle. Down that road it's difficult. Not impossible, but there are lots of problems. No, it's a field equation and it's invariant. So we're going to use this observation here, the Dirac equation is invariant under Lorentz transformations, to build a Lagrange density in the next lecture. And then also we'll start solving this Dirac equation and building a quantum field theory soon afterwards. So, I won't do that today. That needs me to introduce a little bit too much notation. So I think at this point I'll stop. Thank you very much.